Welcome back everyone, and we as always start with our warm-up quiz. So pens and paper ready to go. So if I gave you this graph with force on one axis, mass on the other, and it's a straight line graph, what units would I expect for the gradient of the line? What units would I expect for the gradient of the line? So kgs per newton, newtons per kg, or newton kgs. So pause the video now to have a think about it, and I'll move on to the next question. E equals a half mv squared, kinetic energy, shows a squared relationship. If I was to double the speed, the velocity, what happens to the energy? And it's assuming that m just stays the same. So if I double the speed, what happens to the energy? Pause the video there as I'm moving on to question 3. So we've got an ice skater here moving at a constant speed across frictionless ice. So draw the forces, we'll draw a force diagram basically for this. So there's 3 for you to choose from there. This ice skater moving at a constant speed across frictionless ice. Pause the video if you need it. So moving on to question 4. I'd like you to pause the video and draw in the force diagram for the squirrel, and then separately draw the vector addition diagram. So this is a question you have already done, but I want you to do it again to get you, going over it and remembering it. So pause the video, take your time on this one, and then when you come back, let's do the answers. All right, so we've got force on one axis, mass on the other. We work out gradient from rise over run, and the rise is the newtons and the run is the kg, so newtons per kg, and that's where that comes from. For a squared relationship, if I double the velocity, because it's squared, times 2 becomes times 4 for the energy, so it's 4 times bigger. Your force diagram, it's moving at a constant speed, so there must be balance forces, so that all of a sudden gets rid of this one. And it's frictionless ice. So if there's balance forces but there's no friction, this one doesn't work either. It's this one. Hey, here's something. This one's hard to get your head around, and we've done this. If we've done this as a question, it's only got the upwards and the downwards forces, even though it's moving. Which way is the ice skater moving? So it turns out if you have the force diagram and they are moving at a constant speed, if you're not told which direction they're going, you can't work it out at all. They could be going forwards. They could just as well be flying backwards. You don't know, and it doesn't matter. And question 4, draw a force diagram for the squirrel sitting on the roof. So he's not moving. Net force is 0. That symbol means net force equals 0. Force diagram. First of all, we always identify the system. Force of gravity on squirrel by Earth. The normal force is always perpendicular to the surface. So F normal on squirrel by roof. And they're not, if I draw these two together, they haven't closed off to this where the start is. So at the moment it looks like there's a net force here, which doesn't make sense because I've said that the net force is 0. So there must be another force that comes up like this to there, and that is the friction. F friction on squirrel by roof. Great. See you in the rest of the lesson.